In mathematics, the projective special linear group PSL is a finite simple group that has important applications in algebra, geometry, and number theory. It is the automorphism group of the Klein quartic as well as the symmetry group of the Fano plane. With 168 elements, PSL is the second smallest non-abelian simple group after the alternating group A5 on 5 letters with 60 elements, or the isomorphic PSL. Definition: the general linear group GL consists of all invertible 2 times 2 matrices over F7, the finite field with 7 elements. These have non-zero determinant. The subgroup SL consists of all such matrices with unit determinant. Then PSL is defined to be the quotient group SL, I, minus I, obtained by identifying I and minus I, where I is the identity matrix. In this article, we let G denote any group isomorphic to PSL. Properties: G equals PSL has 168 elements. This can be seen by counting the possible columns. There are 72 minus 1 equals 48 possibilities for the first column. Then 72 minus 7 equals 42 possibilities for the second column. We must divide by 7 minus 1 equals 6 to force the determinant equal to 1, and then we must divide by 2 when we identify I and minus I. The result is, equals 168. It is a general result that PSL is simple for n, Q2, unless equals or. PSL is isomorphic to the symmetric group S3, and PSL is isomorphic to alternating group A4. In fact, PSL is the second smallest non-abelian simple group, after the alternating group A5 equals PSL. The number of conjugacy classes and irreducible representations is 6. The sizes of conjugacy classes are 1, 21, 42, 56, 24, 24. The dimensions of irreducible representations 1, 3, 3, 6, 7. Character table where the following table describes the conjugacy classes in terms of the order of an element in the class, the size of the class, the minimum polynomial of every representative in GL, and the function notation for a representative in PSL. Note that the classes 7a and 7b are exchanged by an automorphism, so the representatives from GL and PSL can be switched arbitrarily. The order of group is 168 equals 3 * 7 * 8. This implies existence of Solo's subgroups of orders 3, 7, and 8. It is easy to describe the first two. They are cyclic, since any group of prime order is cyclic. Any element of conjugacy class 3a56 generates Solo 3 subgroup. Any element from the conjugacy classes 7a24, 7b24 generates the Solo 7 subgroup. The Solo 2 subgroup is a dihedral group of order 8. It can be described as centralizer of any element from the conjugacy class 2a21. In the GL representation, a Solo 2 subgroup consists of the upper triangular matrices. This group and its Solo 2 subgroup provide a counterexample for various normal P-complement theorems for P equals 2. Actions on projective spaces. G equals PSL acts via linear fractional transformation on the projective line P1 over the field with 7 elements. Every orientation-preserving automorphism of P1 arises in this way, and so G equals PSL can be thought of geometrically as a group of symmetries of the projective line P1. The full group of possibly orientation-reversing projective linear automorphisms is instead the order 2 extension PGL, and the group of collineations of the projective line is the complete symmetric group of the points. However, PSL is also isomorphic to PSL equals GL, the special linear group of 3 times 3 matrices over the field with 2 elements. In a similar fashion, G equals PSL acts on the projective plane P2 over the field with 2 elements, also known as the Fano plane. Again, every automorphism of P2 arises in this way, and so G equals PSL can be thought of geometrically as the symmetry group of this projective plane. The Fano plane can be used to describe multiplication of octonions, so G acts on the set of octonia in multiplication tables. Symmetries of the Klein quartic. The Klein quartic is the projective variety over the complex numbers C defined by the quartic polynomial x3y plus y3z plus z3x equals 0. It is a compact Riemann surface of genus G equals 3, and is the only such surface for which the size of the conformal automorphism group attains the maximum of 84. This bound is due to the Hurwitz automorphisms theorem, which holds for all G greater than 1. Such Hurwitz surfaces are rare. The next genus for which any exist is G equals 7, and the next after that is G equals 14. As with all Hurwitz surfaces, the Klein quartic can be given a metric of constant negative curvature and then tiled with regular heptagons, as a quotient of the order 3 heptagonal tiling. With the symmetries of the surface as a Riemannian surface or algebraic curve exactly the same as the symmetries of the tiling. For the Klein quartic this yields a tiling by 24 heptagons, and the order of G is thus related to the fact that 24 times 7 equals 168. Dually, it can be tiled with 56 equilateral triangles, with 24 vertices, each of degree 7, as a quotient of the order 7 triangular tiling. Klein's quartic arises in many fields of mathematics, including representation theory, homology theory, octonia in multiplication, Fermat's last theorem, and Stark's theorem on imaginary quadratic number fields of class number 1. Matchy group. PSL is a maximal subgroup of the Matchy group M21, the Matchy group M21 and then the Matchy group M24 can be constructed as extensions of PSL. These extensions can be interpreted in terms of the tiling of the Klein quartic, but are not realized by geometric symmetries of the tiling. Group actions. PSL acts on various sets. Interpreted as linear automorphisms of the projective line over F7, it acts Chapter 2 transitively on a set of 8 points, with stabilizer of order 3, acts sharply 3 transitively, with trivial stabilizer. Interpreted as automorphisms of a tiling of the Klein quartic, it acts simply transitively on the 24 vertices, with stabilizer of order 7. Interpreted as a subgroup of the Matchy group M21, which acts on 21 points, it does not act transitively on the 21 points.